Imagine that our sun is the size of just a single grain of sand. Now our sun is just one of a multitude of stars. It's surrounded by over 200 billion of them in our own Milky Way galaxy alone. Our sun is just a speck in the vast beach of stars. But the Milky Way galaxy is, in itself, just one of 100 billion galaxies scattered throughout the cosmos. It's been estimated that there are more stars in the universe than there are grains of sand on all the beaches in all the world. Just think about that for a moment. The size and scale of the universe is awe-inspiring. But as a scientist, what I find so remarkable is that the human race has managed to deduce so much about what it looks like. Let me try and put this achievement into context. From our vantage point, living on a minuscule speck, orbiting around this single grain of sand, we've managed to deduce the size and shape of all those beaches. To my mind, this is one of the human race's greatest accomplishments, and I'd like to tell you the story of how we did it. This film is the astonishing story of how we gazed upward from our isolated and unremarkable vantage point and began to deduce the shape, size, and origin of everything that there is. It's the story of how we came to understand reality at the largest scale. It's the story of everything. I want you to pause for a moment and think about this one basic question. Here I am, sitting under the night sky. Above me is the atmosphere, and beyond that the moon, and way beyond that the stars. But then what? What's the totality of everything there is? It's a question we've all asked at one point or another. I remember as a kid growing up in Baghdad, during the summer we'd take the beds up onto the roof, and I remember lying awake at night looking up at the stars and wondering whether space went on forever or whether the universe had an edge. Today we are beginning to understand just how complex this question really is. But 500 years ago, it seemed like there was a very simple answer. You see, the prevailing belief was that the Earth was enclosed in a vast but thin shell of rotating stars that were fixed in position. When you look up on a starry night, it's not difficult to see why people believed we lived within this shell. But in the 16th century, something happened which would shatter this view of the universe. It was an event that would set the human race on a journey to uncover the true size and shape of everything. This is a Type 1, a supernova, an exploding star. It's an event of almost unimaginable scale. It shines 5 billion times more brightly than our own sun. In 1572, a supernova like this would have become visible on planet Earth. At the time, it was known simply as the phenomenon. And to anyone who saw it, it must have been an extremely shocking and mysterious sight. This new light in the night sky shone more brightly than Venus and even became visible during the day. It's not surprising, then, that many sought a religious explanation for this bizarre and troubling event. One possible interpretation of the new star of 1572, which was put forward by some intellectuals, was that this was the star the wise men saw 1,570 years earlier. It's the star that shined over Bethlehem, and it's now returned. So something as cosmically important as the incarnation of God on Earth might be being proclaimed by this new star. The phenomenon fascinated and mystified many people across Europe, and in England it fired the imagination of the MP of the sleepy Oxteter town of Wallingford. His name was Thomas Digges. But just as Digges began to study this mysterious new star, it started to grow dimmer. Digges' friend, mentor, and fellow astronomer, a man named John Dee, reasoned with him that this phenomenon could be a moving star, something previously thought to have been impossible. Perhaps it had grown brighter as it approached the Earth and faded as it had gone away. Now, although this theory was wrong, it got Digges thinking about the true nature of the stars that surround the Earth. It began to seem very unlikely that they were all arranged in a vast, thin shell. Maybe this apparent shell was just an illusion. It would take Thomas Digges another 4 years before he published his strange idea. And when he did, it was in the form of a simple diagram added to a translation of the works of Nicholas Copernicus, the man who'd first argued that the sun was at the center of the universe. Have a look at this. On this side is Copernicus's model, absolutely revolutionary. It has the sun at the center, with the Earth in orbit around it, along with the other planets. And then the outermost shell is that of the fixed stars. On this side is Digges's diagram, included in the English translation. Exactly the same, but he's taken Copernicus's stars out of their fixed shell and scattered them out into endless space. Digges's diagram was describing a radical new picture of the cosmos, one where the stars in the night sky now existed in an infinite space. Digges shows it unlike Copernicus. Digges shows it as being infinite. This is a sphere, he says, of the stars fixed infinitely up. And that is a moment when perhaps Europeans start to think of the world as unbounded, as infinite, as a world without end. Digges's new picture of the universe was revolutionary. Previously, we'd been contained within a small shell of stars. Now, we were suspended within an infinite, static universe. But this picture of everything produced a strange paradox. If this infinite universe contained an infinite number of stars, then why was it dark at night? In the traditional old-fashioned view of the universe, this universe was infinite and static. It was very soon recognized that a static, infinite universe was ridiculous, and that is because in such a universe there would be an infinite number of stars, and every line of sight from ours would intercept one of these stars. A static, infinite universe could not be dark. It should be glowing as bright as the sun, and we know that's not our universe. Our universe, the night sky, is dark. Although Thomas Digges first raised this question, the problem came to be known as Olbers' paradox. As simple as the question sounds, it would take until the 20th century to find a truly satisfactory answer for why the night sky is not as bright as the day. Solving all this paradox would require many great scientists who weren't afraid to think differently, radically differently. You see, solving the paradox is all about understanding the shape, size and origin of everything there is. Without this understanding, the puzzle would be impossible to solve. You see, stuck here on Earth, we don't have access to interstellar travel, so we have to allow our minds to make that intellectual leap. By simply looking up, Digges and his contemporaries had begun a scientific journey to understand what everything might actually look like. But for 200 years after Thomas Digges' insight, little progress was made in understanding the most distant reaches of the cosmos. At the end of the 18th century, however, all that would change. Until the end of the 1700s, everything that lies outside the solar system is, for astronomers, pretty uninteresting. Astronomy until then was the science of our system, of the Earth and the planets, satellites and comets, and the stars were a kind of glorified and rather interesting backdrop. This changes around 1800. This small and unremarkable house in Bath was once home to the astronomer William Herschel and his sister and devoted assistant, Caroline. Together, they would develop and build a new generation of telescopes that would allow them to see further out into space than any human had ever done before. William Herschel was born in Hanover, but moved to England in 1761 to pursue a career as a musician and composer. But he soon developed a passion for astronomy and began building telescopes in his spare time. Herschel soon perfected a technique for producing telescopes borrowed from Sir Isaac Newton. The telescopes used metal mirrors that were capable of capturing much more starlight than the glass lenses that were popular among other astronomers. This tiny room at the back of Herschel's house used to be his workshop. It was here that he'd smelt various metals together in the furnace to make the reflecting mirrors for his telescopes. And he would experiment with different metals, different combinations, to get them as reflective as possible. Then, with Sister Caroline to help him, he'd spend literally hours on end polishing the surface of the mirrors to achieve the precision required. And let's remember, this is quite a dangerous, confined environment. The floor still bears the scars of the molten metal that they'd spilled, cracking the paving stones. With his powerful telescopes, Herschel and his sister Caroline would scour the heavens night after night, cataloguing the stars. The universe they were seeing was revealing itself to be one of dynamic complexities, a universe of natural organic motion, a place of endless wonder. Herschel's revolutionary telescope design made him famous. With it, he'd discover a new planet, Uranus, a discovery that would earn him the job of the king's astronomer. Now, this new role gave him the time and resources to start a much grander task, to try and map all the stars in the universe in an attempt to draw a picture of everything. Soft music. In 1785, Herschel published this remarkable image. It shows an approximation of the Milky Way, with our sun residing at the center. Herschel had seen that we are part of a vast disk of stars, a huge galaxy of suns that seemed to have a clear boundary. It appeared as though Herschel's craftsmanship had actually allowed him to see to the edge of everything. But soon, a nagging problem began to emerge. Dotted around the sky, Herschel and others had been observing strange cloud-like objects known as nebulae. Some of these nebulae seemed to have distinctive form and complex structure. Some astronomers began to suggest a radical idea. Perhaps the Milky Way wasn't everything that there was. Perhaps some of these nebulae were, in fact, gigantic galaxies of stars just like ours that actually existed in deep space. Unfortunately, there was no way to answer this question satisfactorily. The problem was that for all Herschel's great technological achievements, and for all those long, cold nights that he spent with Caroline outside, gazing painstakingly at the heavens, there was one problem they couldn't solve. They had no way of accurately measuring distances in outer space. It wouldn't be until after Herschel's death that the cunning method was developed to measure the distances to objects deep into space. The technique was known as stellar parallax. If you look at an object like your finger from two vantage points, it will shift in your frame of reference. By observing how much it shifts, you can calculate how far away it is. My finger is moving a lot more between each frame than the building that's behind it. Now, an astronomer called Friedrich Bessel worked out that if you took images of stars when the Earth was at either side of its orbit around the Sun, it would be possible to actually see the stars shifting. By observing how much they shifted, you could then work out their distance from us. Bessel calculated that the relatively close star 61 Cygni must be some 100 trillion kilometers away. But, amazing though this technique was, it was still very severely limited. The diameter of the Earth's orbit is 300 million kilometers. This means the parallax method can only measure objects out to about 300 trillion kilometers, only a tiny fraction of the size of the Milky Way. It soon became clear that there was plenty in the heavens that was practically impossible to measure, particularly those mysterious nebulae. They would remain an enigma until the beginning of the 20th century, when they ignited a great debate. One group of astronomers agreed that there is only one galaxy, ours, the Milky Way, and everything else we see, the globular clusters, the nebulae, are all somehow inside that galaxy. Then there were other astronomers who argued no, many of these nebulae are themselves giant island universes, unimaginably far away from us. There was evidence on both sides. This mystery remained a source of bitter debate until the beginning of the 1920s. The woman who would help solve the problem is one of the great unsung heroes of science. She worked at the Harvard College Observatory, and her name was Henrietta Leavitt. Leavitt's job was to count and catalogue the stars. producing images from observatories around the world. She was a brilliant scientist who loved her work. This is one of the photographic plates of space that Leavitt worked with. You can see her bright mark highlighting tiny details within the image. With meticulous care, hundreds of subtle features of stars have been noted. It was this ability that would help her come up with an ingenious idea, one that would help unravel the true size of the universe. The idea rested on finding an objective way of defining the true brightness of a star. Leavitt became fascinated by a type of star known as a Cepheid variable, which pulses in the night sky. Her breakthrough was discovering that their brightness was precisely related to the speed they blinked. Let me explain. These two stars are blinking at the same rate, which means they should be exactly the same brightness. If one star appears dimmer, you can then calculate how much further away it is than the brighter one. Leavitt's method meant that she knew the true brightness of the Cepheid variable. She'd found a way to measure the distance to stars that lay far beyond the reaches of parallax. But without access to a telescope, she could go no further with her work. She was forbidden from working in the supremely male-dominated world of the observatory, but her discovery now gave astronomers a tool to measure the distances to the mysterious nebulae. The idea that our Milky Way might contain everything that existed was about to crumble. The scale of the universe is really only understood amazingly recently. In the 1920s, it was absolutely plausible that the universe consisted of one galaxy. Some of the best astronomers in the world, in the US for example, seriously held that view and had good evidence that it was true, and they were wrong. The evidence to finally settle the great debate would be found thanks to the powerful new Hooker telescope being built at the Mount Wilson Observatory just outside Los Angeles. Using this incredible piece of technology and Henrietta Leavitt's ingenious method for calculating distance, a young astronomer would make a discovery that would change our view of the universe and forever immortalize his name. The astronomer was called Edwin Hubble. Hubble was a very different kind of scientist compared to Leavitt. He was a larger-than-life character, an extrovert with a huge ego, but he was still a hugely talented and visionary scientist. He was born and grew up in America, but spent some time in England, and this seems to have left a lasting impression, as he'd be heard walking around the observatory shouting things like "By Jove" and "What ho" in a completely over-the-top British accent. The talented, passionate, and eccentric Hubble rapidly gained a name for himself in the world of astronomy. But it wouldn't be until 1923 that he would discover something in what was then known as the Andromeda Nebula that would reveal the true scale of our universe. I've come to the University College London Observatory to meet astronomer Dr. Steve Fossey to see for myself just what Hubble's revelation was. We're going to key in the coordinates for Andromeda to the console here. So 0 hours 43 minutes. For Hubble and his assistant Milton Hummerson, studying Andromeda was a long and painstaking process, but today we can quickly locate and photograph it in great detail. So this is an image that we took a couple of weeks ago. Right. And if I zoom in, you'll see just there is the Hubble sphere, the first sphere that he found that unlocked the whole problem. Because presumably, that's when he could use Leavitt's method of working out how far away it is. Exactly. Once he'd seen this and identified it as a variable, he then had the key to determining just how bright that object really was, and worked out that it couldn't have been in our own galaxy. It had to be millions of light years away. Absolutely, that's exactly it. And you see the nuclear region, but as we adjust the contrast here, I can stretch the contrast just to bring out some of the detail in the galaxy.
Yep. You see dust lanes in silhouette against the billions of stars that are within Andromeda there.
By finding one of the variable stars in Andromeda and measuring exactly how long it took to pulse, Hubble was able to use Leavitt's work to calculate exactly how far away it was. This is the photographic plate where Hubble marked his new Cepheid variable star. Using it, he calculated that Andromeda was many, many times more distant than the furthest reaches of the Milky Way. Andromeda was indeed an island universe, a vast galaxy of stars. We now know that Andromeda is over 2.5 million light-years away. This means that the light that reaches us from Andromeda today left on its journey before modern humans had evolved.
That's our neighbor. That's our neighbor. That's our nearest large galactic neighbor. I have to remember that what I'm looking at here is the real thing, using photons that have traveled millions of years to reach my eye.
That's right. These are photons directly from Andromeda that are arriving in my eye. Today, we have the power to see Andromeda as Hubble had only dreamed of. We now estimate that Andromeda contains over 1 trillion stars, and it's just one of a vast multitude of galaxies scattered throughout our universe.
In 1923, the universe had been the size of the Milky Way. By 1924, the space that surrounds us had been revealed to be billions of times bigger and home to almost unimaginable cosmic complexity. Soft music. Hubble had shown that there are a multitude of galaxies outside of our own and had pushed back the boundaries of the universe. But he'd not seen an edge of space. He had not seen everything. There was still no clue as to how big our universe was or even what shape it might be. To understand the strange truth about everything would require more than just observations. It would require mathematics. A powerful new type of mathematics that would be able to describe the bizarre properties of space itself.
When you're trying to understand the universe, it's easy to think that what you do is make lots of observations. See what's there and then fit it all together into your grand picture. But the problem is, unless you have some sort of idea what the picture should be, you don't know what observations to make, you don't know what's significant.
And throughout the history of science, every so often someone has to come up with a new mathematical idea.
The new mathematical ideas about space were so weird, so far removed from common sense that it would take over 2,000 years and the genius of Albert Einstein to formulate them. But when they were ready, these strange new types of mathematics would lead to a revolution in our understanding of the space that surrounds us.
Okay, so what is space? We think we know the answer to this. I can talk about this room being spacious. There's a lot of space in here, or a confined space. There's not enough volume, not enough space.
But does space only exist when there's stuff in it? Does space only have a meaning when it's enclosed by walls? Think of the distance between two objects. Does that gap still exist if you take the objects away? What meaning can we give to distance if it doesn't have a start and end point?
Ultimately, the question is this. Does space in itself have form? Does it have structure or shape? Or is it just a place where things happen? The properties of space were first described by the mathematician Euclid over 2,000 years ago in his legendary text. In it, he laid down a set of simple logical rules about space in what today we call Euclidean geometry.
Euclidean geometry is the geometry we see around us every day. If you're sitting in a room and it's the usual rectangular room, what you see is lots of straight lines, right angles and parallel lines. If you have a window, the two sides of the window are parallel. If you extended them, they'd stay exactly the same distance apart. They would never meet. And the other thing you'd see if you looked a little closer is that any triangle you draw, the angles in the triangle always add up to 180 degrees. And that's characteristic of Euclidean geometry.
People used to think that this was just how geometry was, that nothing else was possible.
For Euclid himself, and for almost all mathematicians for the next 2,000 years, these rules weren't just true mathematically. They were also true statements about physical reality itself. They thought that two parallel lines would remain parallel forever, that a triangle in real space would always have angles adding up to 180 degrees.
But weird as it might sound, many others would refine and develop Gauss's ideas. One of his greatest achievements was giving us a clever method of accurately measuring curvatures. It would become known simply as the remarkable theorem. Let me explain with this globe. You see, we can see that it's three-dimensional because we can stand back and look at it. But what if you were an ant stuck on the surface? How would it know that the surface is curved? So imagine you're the ant and you start off at the North Pole and face south. You move down towards the equator. At the equator, you still face south and shuffle sideways along the equator. Then you reach a certain point and start walking backwards, still facing the same direction, and head back to the North Pole. Now, look at what happened here. You were pointing south all the way around, and yet when you arrive back at your starting point, you're facing in a different direction. Understanding this gives us a way of calculating the curvature of a surface without ever leaving it. This was an amazing insight, but it only applies to curved surfaces, which are two-dimensional. It would take a brilliant student of Gauss's, Bernhard Riemann, to develop these ideas in a way that could be applied to the three-dimensional space that surrounds us. It would be a daring, outlandish, and to non-mathematicians, absurd-sounding concept. Aged just 26, Riemann encapsulated his strange new ideas about geometry in a lecture that would become legendary among mathematicians. In June 1854, Riemann delivered his lectures to an enraptured audience. In them, he detailed how he'd taken Gauss's ideas on curved surfaces and generalized them so that they applied not only to curved two-dimensional surfaces, but the curvature of space in any dimension. Rapid clapping. Okay, so I'm sure this all sounds rather complicated. What exactly do we mean by curved space in any dimension? Let me try and explain. Here's the thing. Gauss talked about curved two-dimensional surfaces. Well, here we have a sheet of paper, and it's two-dimensional, so if I curve it, we can visualize and see this curvature, but only because it's embedded in 3 dimensions. Now, what if we curved 3 dimensions? Presumably, we'd need a 4th dimension. But how do you get to this 4-dimensional space? It's impossible to step outside of our 3-dimensional world. Wherever you travel in the universe, no matter how far you go, you're always stuck in 3 dimensions. The genius of Riemann was showing that you didn't need to stand in a 4th dimension to know that space was curved. You could actually determine it from the inside, but for Riemann, this would always remain a purely mathematical idea. It would take Albert Einstein to tie these mathematical concepts together and apply them, bendy, curved, non-Euclidean geometries, to the real space that surrounds us. I think the most important point about the whole story of non-Euclidean geometry is that it shows how mathematics and the real world are connected. It starts out with mathematicians playing around, asking, could there be a geometry different from Euclid's? And if anyone came to them at the time and asked why they were studying this, they'd say, I don't have a clue. What's it useful for? No idea, it's just interesting. But they prodded around and found a surprising answer. Different geometries were possible. And even then, nobody had any real applications for these ideas. But when the moment was right, Einstein came along and said, that's what I need. That's real physics. Suddenly, this piece of esoteric mathematics became vital to the scientific enterprise. Einstein revealed that we do not live in the flat world of Euclid, but in the strange, curved worlds of Gauss and Riemann. In just a few short years, Einstein went from wrestling with some of the most difficult and abstract mathematical ideas to having dinner dates with Charlie Chaplin. And it was all thanks to the pinnacle of his life's work, the general theory of relativity. In the general theory of relativity, Einstein took Gauss's and Riemann's mathematics and used it to paint a revolutionary picture of the physical world. He showed that, just as Gauss had suspected, the geometry of the space around us isn't always the regular flat Euclidean kind. Now, since Newton's time, gravity was thought to be a force that pulls all objects together. If I drop this apple, it's as though there's an invisible rubber band pulling it down toward the Earth. But Einstein's general theory of relativity gives us a completely different picture. The equations of general relativity revealed that it was the presence of mass that caused space to curve and distort. The reason we have gravity on Earth is because the Earth is actually bending the space around it. In Einstein's theory of the universe, space becomes a dynamic entity that reacts to its contents. Space knows about the presence of gravitating bodies and responds by changing its geometry in intriguing ways. What was, in the 16th, 17th, 18th and 19th centuries, a boring still object, now had a description showing how the space and time we exist in can be warped. They showed that space and time are not the fixed, unchanging stage on which the universe's actions play out. They're part of the performance. It was soon realized that because the general theory of relativity applied to everything, it gave physicists a way to step outside the universe and imagine how it might be behaving in its entirety. And when they did this, they saw something extremely disturbing. The equations painted a picture of the universe that seemed ridiculous. It was expanding. It seemed preposterous that the entire universe could be some kind of moving, organic, expanding entity. It was such a strange prediction that even Einstein refused to believe it. He had overturned common-sense notions of space and time that humans had held for thousands of years. Yet he couldn't accept that the universe might be dynamic and changing. In fact, he was so convinced that it was static. He modified his original equations by adding an extra term called the cosmological constant to stabilize the universe. But Einstein was trying to fix something that wasn't broken. Armed with the Hooker telescope, Hubble revealed the truth that Einstein had refused to believe. After discovering that our galaxy was just one of many, Hubble began studying the movement of other galaxies. Hubble knew that as a light source approaches us, the light waves get compressed and appear blue. If an object is moving away, the light waves are stretched out and appear red. What he saw was astounding. All distant galaxies were red-shifted. They were all moving away from us. Not only that, but the further away a galaxy was, the faster it was moving away. Hubble's observations and Einstein's general theory of relativity were in agreement. But here's the crucial point. It's not that the galaxies are flying away from each other through space, but rather that the fabric of space itself, in between the galaxies, is expanding. So the entire universe is getting bigger. This is what Hubble's and Einstein's work revealed. Einstein soon visited Hubble to see the data for himself. He would go on to admit that changing his equation had been his biggest scientific blunder. So why was space expanding this way? Both Hubble and Einstein soon agreed that if the fabric of space was expanding, it meant that previously the universe had to have been smaller. Rewind the clock far enough back, and it appeared as if there was a point when our entire universe began. The data were pointing towards the moments of creation. But many scientists were not convinced by this apparent Big Bang. It seemed like a leap too far. But there was one piece of evidence that had the power to convince everyone. It seemed that if the Big Bang had happened, then sometime after the instance of creation, a flash of light should have been emitted throughout the universe. Every part of the cosmos should now be filled with this light. And it turned out it was. It just happened to be in a rather unusual form. As unlikely as it sounds, the relic of the Big Bang fireball was actually visible on television. Let me explain how this is possible. Imagine this balloon is our universe. Here it is, just a few 100,000 years old. At this point, something very strange happens. The universe suddenly becomes transparent to visible light as atoms form. It's as though a fog has lifted and light can now travel freely through the cosmos. At every point in space, photons begin to move unimpeded, filling the universe with a blinding light. But this light, released in the hot turmoil of the early universe, didn't remain bright forever. As space expanded, it stretched through the spectrum, from visible light down into microwaves. It's these microwaves that get picked up by television aerials. Remarkably, almost 1% of the static we see on TV is the afterglow of creation itself, stretched remnants of the earliest light in the universe. Using microwave radiation, cosmologists could even date the universe. Our entire universe is 13.7 billion years old. This marked the final piece of information needed to answer a question that Thomas Digges had posed over 400 years ago. Why does it get dark at night? Okay, so here's where it all makes sense. The further away a star is, the longer it takes for its light to reach Earth. If the universe had been around forever, all the light out there would have had time to reach us, and the night sky would be ablaze with starlight. But it's not. Here's why. Imagine that when the universe was much younger and smaller, a beam of light from the other side of the universe began its journey to our vantage point. As space expands, the distance the light must cross keeps growing. Fast forward to today, and this light still hasn't reached us. So no matter how hard we look into the sky, we simply won't be able to see it. We can only observe the stars whose light has had time to reach us in the 13.7 billion years since the Big Bang. This region is known as the observable universe. There aren't enough stars here to light up the night sky, so we only see the stars and galaxies whose light has reached us, which is why it gets dark at night. It's a fact we take for granted. The sky at night is dark, but it's incredibly profound. It took 200 years of theorizing and thinking, and the development of general relativity, before we could understand why the night sky is dark. Through reasoning, observing and imagining, we've found increasingly better ways to project beyond the confines of our small, tumbling rock in space. We've become adept at creating pictures of everything. This is a computer simulation of the universe in its infancy. Using it, we can see how the force of gravity has shaped the cosmos over billions of years. The brightest whites and yellows in this image represent where galaxies and galaxy clusters are forming. As the universe evolves, a strange and hidden structure begins to emerge, the cosmic web. This is our best picture of what everything might look like on the largest scales. It shows vast filaments linking massive clusters of galaxies, each containing trillions of stars. The scale is sometimes hard to appreciate, but it would take light nearly 10 billion years to cross the distance in this image. However, this incredible picture of everything is destined to change. We're beginning to understand that, in the distant future, the universe will become a terrifyingly bleak and desolate place. In 1998, a team of astronomers published a paper in which they studied supernova explosions in distant galaxies. They aimed to measure how fast the universe was expanding with great accuracy. They expected to find that the rate of expansion was slowing down due to the gravitational pull of all the matter in the universe. But they were in for a big surprise. The universe was not just expanding, it was accelerating. The rate of expansion was increasing. There seemed to be some mysterious force pushing everything apart. We still don't understand its origin, but it's been dubbed dark energy. There's a fascinating and disturbing consequence to this. If the expansion of the universe continues to accelerate, our visible universe will start to empty. Let me explain. Imagine I'm in a distant galaxy that you can see from Earth. As the space between us stretches, there will come a time when it expands so rapidly that light can't outrun it, and the galaxy will disappear from view. This means that far into the future, in about 100 billion years, if intelligent life still exists in our galaxy, it will only be able to see the stars in the Milky Way. All the other galaxies will have disappeared, leaving them alone in a vast, dark, empty expanse. I have here a box. What would happen if I removed everything I possibly could from inside it? What would remain in the space within the box? Is it really nothing?